In this video, we are going to look at the central processing unit. And we're going to find out who was John von Neumann. Well, John von Neumann was a Hungarian-born American mathematician. He died in 1957. His work was published in 1945, which was the architecture design of the CPU, and it consisted of the control unit, the arithmetic logic unit, the memory unit, registers, and inputs and outputs. You may have heard of input and outputs, I don't doubt you have, but you're probably wondering, this guy died in 1957. His work was published in 1945. What has that got to do with computers today? What's that got to do with modern technology? This was all before the internet. This was all before laptops and tablets. Well, watch this video and find out how John von Neumann's architecture is so relevant to today's computing. So basically, how on earth is this old theory that was published so innovative back in the day, and why is it so relevant to today? Well, von Neumann's architecture is based on programming concepts being stored in a memory. Now, previously, computers were very mechanical. They didn't have memory, so you would turn them on, they would do something, and then you would turn them off again. Well, you know, in modern computing, we don't do that. We are based on the fact that computers have memory, like the apps that we use. So if you use apps such as Duolingo, it will remember the lessons that you've done before and how you've moved forward. For example, for something as small as, you know, your Fitbit, it remembers the exercise that you took yesterday and last week, and it can show you charts of how you've progressed because of the memory. And this is all still used, as you know, in modern computing today. And this is the basic foundations of modern computing. So we wouldn't be where we are if it wasn't for von Neumann's architecture that was published way back in 1945. It's amazing to see how we've moved on. So in its simplest form, the computer has a processor. So this was what von Neumann decided. A computer has a central processing unit. Every computer you use has a central processing unit, and obviously you've been studying computer science, and even if you studied ICT for some time, that you will know every single computer is a central processing unit. Let's look at something as simple as your washing machine. You don't look at your washing machine and say that's a computer, but it has a computer inside it that has a central processing unit. And the processor has direct access to the memory. So the instructions will be stored on this memory, and then the instructions will go through to the central processing unit. The memory contains a stored program that can be replaced and the data required by the program to function. So for example, on your Fitbit, you may have done a 5 kilometer run. So, you know, your Fitbit may, for example, store that you run this 5 kilometer run, let's just say you run it in 45 minutes. Then one day you've beaten that record and you've run it in 40 minutes. So therefore it's replaced that memory, and then maybe it may adapt to suit you more and your fitness more. So the stored program consists of individual instructions. So again, looking at something as simple as your washing machine at home. Now, if you wanted to turn your washing machine to a certain program, like maybe a 40-degree wash, and it's got to wash your clothes over 2.5 hours and have an extra spin to make them come out, you know, a bit more dry, then your washing machine and the motherboard inside your washing machine and the memory has stored that program, and those instructions go through the CPU for it to work. Then the processor will execute the instructions in that correct order. Okay, so obviously first your clothes have to be washed before they can have the fabric softener and then spin. Now let's look at the architecture. So there's a central processing unit. Now those of you that would have studied ICT previously will know that's a central processing unit. But we're doing computer science, so we go into a little bit more depth and see how the architecture is made up. You have the control unit. Then you have the arithmetic logic unit, the registers, and in the registers section you've got your individual registers, which are the programming counter, the CIR register, obviously we go through these in detail, the AC, the MAR and the MDR. Now I'm going to go through all of these registers during the course of this video, so you'll see what they are. Then you've got your input device and your output device, and then you've got your memory unit, which feeds to and from, and then obviously the instructions. So as you can see, here's your input device. So anything that you put into the computer, such as your mouse movements, your mouse clicks, and your typing from your keyboard, obviously goes into the central processing unit. And then all the instructions will go from the memory units into the central processing unit, and you can see they go backwards and forwards, and then they go to the output device. Okay, so the output device could be your monitor, it could be your speakers. So central processing unit in your computer, so this is where it is. Okay, so you can see it's under here, and that is as small as it is, and some of them are, well, a lot of them are much smaller. That is the brain of your computer. Now, no computer or embedded device can work without a central processing unit. It's that simple. If you don't have a brain, you can't work, and it's the same with your computer. Now, the CPU is just simply a microchip installed on the motherboard, and it will perform all the calculations and the coordinates for that hardware to work. And it's basically just this tiny electronic circuit that is responsible for executing all the instructions of the computer programs. So this tiny amazing thing is responsible for all of your calculations and all of your computer programs to work. So looking at our arithmetic logic unit, which is here, what is this part? Well, the ALU is the arithmetic, which will add, subtract, multiply, divide, and so on. And then also it works the logic in your computer, such as and or not, and operations to be carried out. So remember, the computer only knows two things, that's ones and zeros and how they're executed. Then you've got your control unit, and a control unit basically controls all the tasks that the arithmetic logic unit controls. Okay, that's with the input and the output devices, and it tells them how to respond to the program. So this one does all the logic and all the arithmetic, but this one will control what this one does and tells them how to respond. And these all basically get interpreted from the memory unit. Now the control unit will provide some of the timing of the signals to be required, okay, because you can't execute everything at once. Some things will take the priority. Okay, so some things may need to happen before something else happens. So the control unit will decide basically the sequence and the signals that are required for your instructions to happen. Now, this is all to do as well with the system clock. Okay, so as I said in this previous slide here, the control unit will decide who, what, where, when and why this is all going to happen. And for this to happen, we need a system clock. So this is the vital part of the unit, okay, because it needs to synchronize the process of the instructions. and like they have a running order. Okay, so there's two clocks. There's an internal clock, which controls the cycle of the activity within the processor, and then there's the external clock, so your system clock, which controls the activities outside of the processor. Now the CPU will basically decide the frequency of the clocks, and this is known as clock speed. So it's not going to happen second by second. Thousands of instructions are processed per second, so they need to be synchronized. So they're not all happening at once, or some are happening before others should. Now, the frequency of this is dependent on the minimum time period required to separate, obviously, each activity. Now, as I said, we was talking about the registers earlier. So there's two types of registers, and that is the general purpose register, the special purpose register, and we need to know the difference between the two. Okay, so special purpose registers is very, very simple. They will have one specific job to do, and they're designated solely for that purpose, whereas the general purpose registers hold the data and the addresses, and they're used in the arithmetic logic operations. So they kind of do quite a lot, okay? So they decide, so like basically they're the ones that are keeping everything going, and then the special purpose registers do one job and one job only. So you've got your accumulator, that's obviously in the arithmetic one, the data register, and the base register for the general purpose. But the ones that we need to know, and you've got your counter register. The ones we need to know basically are the special purpose registers. So the instruction register, the memory address register, the program counter. So looking at our examples of the registers, so we've got the current instruction register, and this stores the current instructions while they're being decoded and executed. Okay, so that's the CIR. So while these are being decoded and executed, the CIR will store them. Then you've got your index register, and that stores a value that's only to be used for indexed addressing, and your memory register that stores the address of a memory location which is about to have its value read or written to. Continuing with our examples. So we've got the memory data register, or it could be known as the memory buffer register. And what this does is that it stores data that's just been read from the memory, and it's about to be written to the memory. Then you've got the program counter, and that stores the address of where the next instruction is to be read from. And then you've got your status register, and that contains individual bits that are either set or cleared. Now, if at the moment you're just like thinking, I don't know what's going on, don't worry, because this is what we need to know. So I'm going to go more in depth discussing these registers right now. The program counter, the CIR, the AC, the MAR and the MDR, and you'll become clearer. So, the role of the program counter. Now obviously everything you do on a computer, such as move the mouse, press a character on a keyboard, maybe you're playing a shoot 'em up game, you're shooting somebody, everything you do is an instruction, and it has somewhere to go, and it has to be stored somewhere. And this is the whole point of the CPU. So for example, like my brain there just maybe went blank, and maybe my memory buffer kicked in and said, hold on, you need to think about this before your mouth opens. So everything you do has to be stored somewhere. So for example, when you was a baby, before you could learn to walk, you crawled. Before you could run, you learnt to walk. So your brain has to store these instructions somewhere. Now, this is the role of the program counter. Now, it's a special purpose register and it has one specific job. And that's when the register has a location of the instruction. Okay, so something's been registered, something's happening, that instruction has to go somewhere. So, and it has to be executed at that particular time. So what the program counter does is that it fetches the instruction and then it increases the counter by 1 and says, right, this is one instruction that needs executing, this is number 2, this is number 3, this is number 4, and it basically counts all the instructions that need to be executed. That's all it does. Then after the instruction has been fetched, the program counter points to the next instruction within that sequence. So right, it's fetched instruction 1, now it's going to fetch instruction 2. And when the computer is restarted, basically the counter reverts to 0. So sometimes, as you know, maybe your phone needs to be rebooted because maybe there's just too many instructions that need to be executed and they've all got backed up. And then what you would do is you'll probably close all your programs, you will restart your phone and then it goes back to 0 and it starts to work properly. Now, we've got the role of the MDR, okay, or maybe it's the MAR. No, sorry, it's the MDR, sorry. Memory Data Register, okay? So basically what we've got to think about is the CPU, yes, it's one big brain, but what we're doing right now is we're dissecting that brain and we're looking at all these different bits and what they do and what their role is within the brain of the computer. So it's a special purpose register and it holds data that is being transferred to or from the memory, okay? So what it does is that it holds that data just in a place for the moment, and then it basically works like a buffer, okay? So it queues the instructions. So maybe think about it like this. There's a lot of people standing at the bus stop and a bus comes along and some people get on that bus, but some people don't because that's not the right bus for them. So they wait and then another bus comes along and then they get on the bus. So it's basically queues the instructions. And it's a two-way register because some data may go from there to the memory and then some data to the CPU. So when the data is fetched from the memory and placed onto the MDR, it is written to go in one direction. Okay, but when there's written instructions, the data is then placed into the MDR from the CPU register and then it puts it into the memory. Okay, so it is just a buffer. It's just like a meeting point for the instructions. Now we've got the MAS. This is the Memory Address Register. So it's a special purpose register. It holds the memory location of the data that needs to be accessed. And it temporarily stores the address location of where the data needs to be sent. Okay, so as I said, this could be any data. Okay, this could be, like I said, inputs on your keyboard, movements of your mouse, or maybe you want to watch a video. Okay, so this could be anything, but it's all an instruction and it needs to be executed and then it goes into the program counter. So as we know, the program counter fetches the instructions and then it puts its counter up by 1. Now we've got the index register. And again, this is the next special purpose register. And this is the circuit that receives and stores and the outputs of the instructions, changing codes in a computer. Okay, so it's also known as address modification. So basically what happens is, as we said, the circuit that receives, stores and outputs the instructions, and maybe the codes might need to change. Maybe something, I don't know, has been updated, something has been modified, and this is what the index register does. So it basically indexes all these instructions. Then we've got the current instructions register. This is the CIR. and this holds the current instruction to be executed. So after having been fetched from the memory, so this instruction's been fetched from the memory, and it is the current instruction that needs to be executed. So this needs to go through. And then the processor will copy the instruction code from the program memory to the instruction register, ready for it to be executed. So now what can happen with that instruction is that it needs to be decoded or interpreted. Now what that means is what is supposed to happen. If you click on, Google Chrome, should your browser open up? Okay, so if you send something to print, should it come out the printer? So now this is combinational in terms of the logic block, which sets up the processor, and then it controls the lines of instructions as required. Now finally, we have the role of the status register. So what this does is this helps to control the flow of the program. So for example, if the code might be checking out, and if instruction on whether to run the next bit of code or not, or will it indicate to say whether it's true or not. So for example, if you're driving a car and you go to a traffic light and a traffic light is about to turn red, should you stop or should you continue to go? Okay, so obviously the red light means you should stop. And this is what the role of the status register does. Is this bit of code going to be executed, or is it not going to be executed? So it basically stores the error flags. So for example, if a calculation is unintended, then it divide it by 0 to cause an overflow of the flag to be set. So it's like, no, this isn't correct, stop. Or yes, this is correct, carry on. Right, now hopefully you've got enough information there to continue to create the tasks in your book now. If you need any more help, please refer to your textbook. Okay, thank you for watching. If you are not one of my students, or you are one of my students, please subscribe. Visit my shop on Tess if you're a teacher for my resources. And follow me on Twitter at Miss Price, SCSI. Thank you for watching.